Right now, something almost 48 feet wide is moving beneath a busy stretch of sea in eastern China. It isn't a submarine, it's carving a railway tunnel. And one day, passenger trains are supposed to travel through the tunnel at up to 155 miles per hour. The tunnel will stretch about 10 miles beneath the Jintang waterway. But last week, the machine had to stop for a problem no normal train passenger will ever see. 104 cutting tools needed inspection and servicing under extreme pressure. The operation lasted 21 days, and outside that chamber, water pressure reached about 7.8 bars. Routine maintenance had become something closer to deep-sea diving underground. And that is only one of the problems this tunnel has to solve, because above them are ships, seawater, pipelines, docks, and one of the busiest kinds of terrain engineers can face. And below them, the ground changes again and again. The Jintang Tunnel connects the Ningbo side of the coast with Jintang Island toward Zhoushan. The complete tunnel is 16.18 kilometers long, just over 10 miles. More than 11 kilometers of that distance is being excavated by giant shield machines, and they aren't digging from one end. Two machines are coming toward each other. One machine is called Yongzhou, the other is Dinghai. Eventually, the plan is for them to meet beneath the seabed. To understand how difficult that is, look at the size of the machine first. The cutterhead is about 14.6 meters, or nearly 48 feet across. Dinghai weighs roughly 4,350 metric tons before you even think about the tunnel behind it. Yet, calling it a giant drill misses what a shield machine actually does. It excavates the ground in front, removes the broken material, pushes itself forward, and builds the permanent tunnel wall behind itself. Those curved concrete pieces arrive one at a time. The machine places them together to form a complete ring. Then the TBM pushes against that new ring and repeats the process. Dig, remove, line, push, repeat, for miles. The machine is essentially a moving underground factory. But the factory has one wall it can never control: the geology ahead. Across this route, the ground transitions repeatedly between soft and hard formations. Some sections behave more like soil, others are brutally strong rock. The hardest material has been measured near 191 to 200 megapascals. In plain English, some of this rock is more than 6 times stronger than ordinary concrete. That difference matters because the cutter that works beautifully in soft ground may struggle badly when hard rock arrives. Hard rock attacks the machine through wear. Every rotation can grind material from the cutting tools themselves. Eventually, a tool that used to break rock becomes another piece of equipment that needs replacing. Normally, engineers would stop the machine and walk to the cutterhead. Under the sea, that simple sentence becomes dangerous, because the excavation face is being held against enormous groundwater pressure. At its deepest, the Jintang project reaches roughly 256 feet below sea level. Peak water and soil pressure is around 8.5 bars. Under conditions like that, opening the wrong door is simply not an option. Pressure must be balanced before people can safely enter the working chamber. And pressure affects the human body, not just the machine. At high pressure, ordinary air creates physiological problems engineers cannot ignore. Nitrogen can affect thinking. Too much oxygen under pressure can also become dangerous. Then there is decompression, the problem divers have dealt with for generations. Come back to normal pressure too quickly, and dissolved gases can form dangerous bubbles inside the body. Traditional pressurized TBM work therefore becomes painfully slow at extreme depth. The deeper the job, the more time can disappear into compression and decompression instead of actual maintenance. So engineers borrowed an idea from an entirely different industry: saturation diving. Saturation divers don't decompress fully after every short underwater job. They remain at pressure for a period, work repeated shifts, then decompress in a controlled process. Jintang's team adapted that principle for a machine buried beneath the seabed. The system has been nicknamed the Deep Sea Space Station. Despite the nickname, this isn't science fiction. It's pressure control, life support, gas management, and careful procedure. Workers can live inside a pressurized module, transfer through another chamber, and travel toward the cutterhead without returning to normal atmospheric pressure each time. That changes how much useful maintenance can happen during one deep intervention. In February, the Ningbo side system completed a 75-meter deep intervention lasting 22 days. That operation replaced 46 cutters. Then this August, the Ningbo side faced another demanding intervention. Workers spent 21 days servicing 104 cutting tools at 8 bar water pressure. Imagine maintaining industrial machinery while the sea is constantly trying to push through the ground around you. That's why sealing systems become as important as the cutterhead itself. The Yongzhou machine uses reinforced sealing designed to tolerate pressures higher than the surrounding conditions. The goal isn't to fight the ocean dramatically. It's to never give the water an uncontrolled path inside. The machine approaching from the Zhoushan side uses another pressure maintenance strategy. Engineers developed a breathing mixture of helium, nitrogen, and oxygen for ultra-high pressure work. Helium helps reduce some of the problems that ordinary compressed air creates at extreme pressure. That system completed a major cutter change campaign this summer. Across 6 work locations, teams made hundreds of pressurized entries. They replaced 67 cutters during that campaign. The operation continued for roughly 75 days. That's what Megaproject engineering often looks like. Not one spectacular moment, but thousands of controlled procedures. Meanwhile, the TBMs still have to stay on the correct path. Remember, 2 machines are digging toward each other from opposite coasts. If each machine drifts slightly in the wrong direction for miles, a tiny error becomes a giant problem. So teams continuously measure position, direction, slope, and the shape of the finished lining. The planned meeting point lies beneath the sea, and the machines are expected to perform an extremely precise underground rendezvous. Planning documents call for the giant machines to meet and then be dismantled underground. That means crews cannot simply drive the machines out through the far end. The tunnel itself becomes the workshop where enormous pieces must eventually be removed. Before that happens, every ring behind the TBM has to remain watertight and stable. Each ring is assembled from several curved precast segments. Those segments are manufactured above ground before ever entering the tunnel. Then, trucks and tunnel transport systems carry them deep underground. Inside the TBM, a mechanical erector picks each piece up. It rotates the segment into the correct position around the circular wall. Bolts, gaskets, and compression turn separate pieces into one structural ring. The next ring locks against it, and the tunnel grows forward one short section at a time. Behind the lining, grout fills tiny spaces between the concrete and excavated ground. That helps prevent movement and supports the ground around the tunnel. Under the sea, tiny movements matter. The machine also has to pass beneath existing infrastructure without disturbing it above. The route crosses beneath pipelines, seawalls, docks, and shipping channels. People on the surface may see almost nothing while a machine thousands of tons in mass passes below. That invisibility is actually part of the engineering achievement. Unlike a bridge, the railway does not need to occupy the shipping channel above. Ships can continue using the water while trains eventually pass below the seabed. Of course, going underground trades visible bridge challenges for hidden geological ones, and Jintang may be one of the clearest examples of that trade-off anywhere. Which raises the obvious question, why spend years doing all this just to put a railway underwater? Because Zhoushan has something unusual for a major Chinese city, it still has no railway connection. The new railway is intended to connect the islands directly into the national rail network. The complete Ningbo-Zhoushan line will run roughly 76 kilometers. Trains are designed to travel at up to 250 kilometers, or about 155 miles per hour. The tunnel is therefore not just an underground road with rails added later. Its geometry has to work for a fast passenger train from the beginning. Curves must be controlled. Grades must remain manageable. Track quality has to keep a train stable at speeds most cars will never legally approach. Ventilation and emergency systems also have to serve a tunnel more than 10 miles long. If a train stops underground, passengers need protected routes and carefully planned procedures. Fire protection, communications, and power redundancy become part of the transportation system. Because once construction ends, the tunnel's real job begins, quietly carrying people for decades. Current plans say the new railway could cut Ningbo to Zhoushan travel to roughly half an hour. Some project information puts the fastest trip at about 26 minutes. That is the payoff hidden behind thousands of cutter changes, concrete segments, and pressure procedures. Construction pain is temporary. Infrastructure is built for repetition. And as of this summer, most of the shield boring section has already been excavated. By late July, project reporting put shield excavation above 10,000 meters. That represented close to 90% of the shield tunneling section. On August 17, Yongzhou alone had advanced 3,936 meters from the Ningbo side. The March project schedule expected the two machines to reach their underground meeting point around the end of 2026. But construction schedules are targets, not promises. Geology can still surprise engineers. Tools will continue to wear. Equipment will still require maintenance. And after breakthrough, crews still have track, electrical systems, testing, and commissioning ahead. Current local planning targets the railway to be ready for operation in 2028. If that happens, Zhoushan's history as a city without railway access will end. That the part passengers will notice most may be the part engineers hope they never notice at all. No pressure chambers, no cutter changes, no rock strength calculations, just a train disappearing into one side of the coast, while ships continue moving across the water above it. Hundreds of feet below, the railway will cross the same channel almost invisibly. And that's the strange beauty of this project. The hardest engineering is being done so the final journey can feel completely ordinary.